I'm going to show you a modification I made to this 18650 module. It corrects a circuit design flaw that restricts how the module can be used safely to power our Arduino and ESP projects. We're going to look at that flaw and a fix for it and examine what we might do to mitigate the flaw without having to modify the circuit. This is called the 18650 Battery Shield version 3, and it operates like a power bank. But power banks require a minimum current draw to keep them turned on, and they usually don't let you power the project while charging the battery. This shield doesn't have either of those limitations, and it's cheap, so it's looking pretty good. It has a micro USB input port, through-hole connectors for 3 volts and 5 volts, and a Type A USB port with 5-volt output. There's a switch that controls just the Type A port output. The circuit uses the popular TP4056 lithium charger IC with added protection and an 18650 battery, 3 ganged 3.3 volt linear regulators, and a switching 5 volt boost converter. The 4096 is set to provide 600 milliamps of current, which can be used to charge the battery or power the load or both. And that's really the problem. All the current coming into the shield from your mains powered USB charging brick goes through the charger IC, and that means the battery charging algorithm can be confused by the load current drawn by your project. This happens in 2 ways. The first problem is when the shield is being used in UPS mode as a backup to mains power, and an extended mains outage has deeply discharged the battery. When power is restored, the TP4056, to protect the battery, will limit its charge current output to 10% of the full 600 milliamp charging current until the battery has been brought above 3 volts. This diagram for the datasheet shows a 1 amp full charge rate, but remember that the shield is set for 600 milliamps, so the 10% value for the shield is 60 milliamps. If the load itself draws more than 60 milliamps, the battery voltage will never rise above 3 volts, and the battery will never be recharged. You'd have to manually disconnect the load for a few minutes to allow the battery to get above 3 volts, and then reconnect. That makes this shield unsuitable as a backup UPS for any load current above 60 milliamps because it wouldn't recover automatically from a deep discharge when power is restored. And to make matters worse, the switching boost converter will draw a higher input current than the output current it's delivering. The lower the input voltage, the more current it needs to draw. So a 60 milliamp limit at the charger could translate to a 40 milliamp limit on the actual project current, or even lower. The second problem occurs at the end of the charging algorithm and is more serious. The TP4056, like all lithium chargers, terminates charging at the end of the constant voltage stage when it detects that charging current has dropped below that same 10% level. But again, if load current is more than that, the current draw seen by the charger will never fall below the 10% level. That means charging will never terminate, and the charger will continue to output 4.2 volts indefinitely. It is not safe to continue to apply 4.2 volts to a charged lithium battery. That's why all lithium chargers terminate charging rather than trickle charge at 4.2 volts. So be warned, this is a safety issue. And even if your project draws less than 60 milliamps, so proper termination does take place, you find yourself in the odd situation where the power brick is plugged in, but the battery is powering the load. That's because the TP4056 actually terminates charging, and that turns off all charger current. So the battery then takes over and powers the load until it discharges down to about 4.1 volts, at which point the TP4056 will kick in again. So you continuously cycle the battery between 4.1 volts and 4.2 volts when the charger brick could have been powering everything if the circuit had been designed right. So the bottom line is, if the mains power brick is plugged in, it's not safe to use this shield with any project that draws more than 60 milliamps through the charger. If it draws less than that, it will work, but battery cycling may still take place. The fix for all this is to modify the shield to add what is formally called a load sharing circuit. It allows the power brick to power the load directly instead of going through the charger IC. The charging algorithm of the TP4056 will not be confused by project current because no project current ever flows through it. One form of load sharing circuit is just two diodes. In this situation, the power source with the highest voltage always powers the load because the other diode becomes reverse biased. And here, if the power brick is not present, then battery current will flow through the battery diode to the load. If the power brick is present, the battery diode will be reverse biased and no current will flow through it. Note, however, that the power brick will also independently provide charging current for the battery if it's needed. We can improve the two diode circuit first by using a Schottky diode in the brick power line, and second by replacing the battery diode with a P-channel MOSFET and a gate resistor, which perform the same function as the diode, but with almost no voltage drop. That will maximize battery life. So here's the circuit we end up with. The MOSFET will be turned on when its gate voltage is brought low with respect to the source. The pull-down resistor does that when the power brick is not plugged in. The battery then supplies current to the load, and the voltage drop will be something less than 1/10 of a volt. But when the power brick is connected, the gate voltage is brought high, which turns the MOSFET off. And the MOSFET is oriented so its body diode will block high voltage from flowing from the brick back into the battery. So in summary, with the load sharing circuit installed, when the power brick is plugged in, it will always directly supply all of the current to the regulators, and at the same time it will independently power the TP4056 to charge the battery all the way to a proper termination, with no subsequent battery cycling. The battery will power the load only when the power brick isn't supplying power. The 60 milliamp current limit is no longer relevant because no load current ever flows through the 4056. I've also changed the function of the manual switch. In its original position, it turned off only the 5-volt supply to the output USB port. That meant the only way to stop the regulator's idle current from draining the battery was to remove the battery. Well, that's inconvenient, and it also exposes us to the risk of reinserting the battery backwards, which could destroy the circuit. So instead, we now use the switch to cut off all power going to the regulators, which would turn off both the shield and any connected Arduino. Now there should never be any need to remove the battery. And you can also still charge the battery even with the switch turned off. The MOSFET I selected is the DMP 1045U. It's a surface mount part, which you can see right there. And so it requires the use of an SOT23 to dip adapter. For the Schottky diode, I selected the SB220. That's a 2 amp Schottky diode. And you'll also need, of course, an 18650 battery of some kind. All 4 items can be ordered from DigiKey. The DigiKey battery is a flat top and unprotected, which is perfect for this shield. And of course, you need the shield itself, which is available from eBay, AliExpress, and Banggood. I assume you already have the resistor and a mains-powered 5-volt charging brick. It should be a minimum of 2 amps, and you need also a cable to connect the brick to the micro USB input. You should not connect the shield to a USB port on your computer. It draws too much current for that. So now let's take you through the mod itself. Here's positive and negative images of the bottom of the shield's PCB. The negative image shows what's going on more clearly, I think. And images laid out in this way remind me of a famous object which also revealed its mysteries in a negative image. So I'm going to refer to this module from now on as the Shield of Turin. Anyway, the first step is to solder the MOSFET to the SOT23 adapter. One way to fix the MOSFET in place ahead of soldering is to first tape down the adapter to your working surface, and then tape the MOSFET in place on the adapter. Then apply a very small amount of super glue along the side of the MOSFET with a toothpick. When that's dried, you just remove the MOSFET tape and solder very carefully. In red here, we have the output of the TP4056 going first to the 3.3 volt regulators and then to the 5 volt regulator with the positive battery terminal right in the middle. Since we need to break any direct connection from the battery terminal to the load, we'll have to remove the battery holder. Use a desoldering braid to remove most of the solder from the holder terminals. And then place your soldering iron tip on the tinned area right next to the terminal. And after a few seconds, you should be able to pull the holder free. And then clean up both sides with braid. And you'll do that at both the positive and the negative end. Next, we have to cut 2 traces on the bottom side of the PCB to break existing connections, and then scrape the solder mask off of 4 traces so we can solder new wires to those scraped areas. Then we have 1 more trace to cut, but no scraping, back on the top side of the PCB. To begin the new connections, solder a wire from the middle of the pin, from the middle pin of the switch to the point where the positive battery terminal used to come through the board. I used solid 22 gauge hookup wire. Next, we connect a wire from the V-bus pin of the Type A USB port to the scraped trace in the 5 volt area. Alternatively, you could just forget the scraping there and use the 5 volt through hole that's already there. Then connect the diode from the scraped trace back near S1 to the top pin of the switch. You'll have to add an extension to the anode lead of the diode so it will reach. Now connect a wire from the source of the MOSFET to the scraped trace near the switch. Enter the through hole of the SO23 adapter from the bottom. Next, connect a wire from the anode end of the diode to the gate of the MOSFET. Come up from the bottom of the through hole and leave extra length sticking through. Then wrap the resistor wire around the extra length. Solder both wires to the adapter and trim any remaining extra length. Connect the other end of the resistor to any convenient ground connection. Next, we're going to connect a wire from the scraped trace on the TP4056 output to the drain of the MOSFET from below with extra length. Cut a length of wire 3 inches long, wrap it around the extra length, solder both wires to the adapter, and trim any excess. Now run the 3-inch wire through the hole at the corner of the board, and this will go to the positive battery terminal. And finally, on the top side, bend the positive terminal of the battery holder so it would lay flat on the tinned area. Then glue a piece of index card or other insulator to the board to cover the tinned area and the original terminal through hole. Replace the negative terminal of the holder in its hole. Cut and strip the wire to the proper length at the positive terminal and solder it to that terminal. Then push the holder down to the board, secure it with hot glue, and then solder the negative terminal in place. Make sure that the positive terminal is connected only to the wire. And that's it. If things go right, you should be able to power loads up to about 1 amp while charging the battery, and the green charging completed LED should come on when the battery is fully charged. If you suddenly disconnect the power brick, the battery should take over immediately and your Arduino or ESP should not reset. Turning the switch off should shut down all output and reduce any battery current to a few microamps. Now, I think this mod is a lot of trouble to go to, and I'm not sure it's worth the effort unless you really need it for a specific project. It's only 3 additional parts, but reworking the circuit to fit them in properly takes time and is fiddly, to say the least. If you don't do the mod, here are some alternatives that mitigate the shield's design flaw, so you can still use it safely. First, use it only for low current projects, that is to say under 60 milliamps. Just make sure it will still recharge automatically if the battery has been drained down to protection levels. And make sure the green LED lights up at some point, indicating that charging has terminated. Second, you could simply go to sleep periodically. Have your project switch to low current draw long enough for the TP4056 to become unconfused. I haven't tried this, but presumably if your project went to sleep periodically for long enough, that would allow charging to begin or to terminate properly, even though the awake current level would be quite high. Once battery voltage gets above 3 volts, or at the other end, once charging current drops below 60 milliamps, the TP4056 won't drop back to the previous state if the load current then goes back high. So this is a real possibility for what would normally be a high current project to still work with this without modification. And thirdly, you could just adopt the rule that you'll never charge and power at the same time. You would always turn off the project when you're charging the battery. This limits the shield to being just a rechargeable battery power source, but that's useful. The 60 milliamp limit doesn't apply. You can draw as much current as the battery and regulators will provide. I guess for the projects I designed, which are typically very low power, these would work well enough for me. But it's good now that I have a modified shield that will work with really anything and work properly. Now, as is usually the case, here are some warnings and caveats if you decide to go forward with this. Do not do this mod for a solar-powered project. The load sharing circuit depends on the 5-volt input being either fully on or fully off, but the solar power will wander, and the circuit may not act correctly or safely. Next, do this mod only if you're using a 2 amp or greater mains power brick as input. With the mod, the shield can draw 600 milliamps charging current plus up to 1 amp of project load, and the brick has to be able to provide both of those at the same time. Next, do not connect the shield to your computer's USB port. I said this before, but I say it again, it draws too much current for that. Then, as was mentioned earlier, be careful inserting the battery. There's no reverse polarity protection in the battery part of the module, and if you insert it backwards, your module will probably be destroyed. And finally, please note that I am a hobbyist and not an engineer. While I believe what I've said here is true, I could be wrong. So you proceed at your own risk. I'll submit this video to my local open source hardware group's YouTube channel, but will probably not be able to respond to comments there. But there will be threads on the Arduino and EEV blog forums where I participate. Just search for 18650 battery shield, or, the Shield of Turin. I'll put relevant links below the video or possibly in a GitHub repo. And many thanks to Andreas Spies for his video number 250, introducing the shield, and to Zach Kemble for his excellent blog post on load sharing circuits. Hope this is useful.